All right, welcome. It is May 9th, and today is class number 8. And today we're going to go over the 65-year cycle, finally, meridional heat transport, and the winter gatekeeper hypothesis, which is too complicated for mortals, and then albedo. So that's our agenda for today. And then next week we'll talk about future climate. So let's get started with share my screen. And we will put it here. 65-year cycle. Everybody ready? All right. All right, I've been promising this for weeks, and it's all based on this, the global ocean conveyor belt, which connects 4 of the world's 5 oceans in a current that is driven by temperature and salinity, not by wind. This is the undercurrent mostly, or the main currents of the ocean. It moves very slowly. It moves centimeters a minute. It takes a given water parcel about 1,000 years to complete its journey around the Earth. So you can see that the sun warms the water in the tropics. In fact, all the way through here, that warm water comes from the Pacific and is shuttled around Africa and stays warm, and then heats up again at the equator here. And then all that warm water makes its way poleward, where it mostly sinks. And this one comes up and gets warm at the equator, right? So warm water getting cold and cold water getting warm. We're going to look at 6 currents today to see how they influence global temperature and climate. So this is the El Nino, the PDO, and that's got a neutral phase where normally the Pacific Ocean, this is all the Pacific Ocean here, moves water westward from, remember all the ocean basins move water westward because of the what effect? Coriolis effect, right? The Earth is moving east, so the water is sloshing west, and so is the heat. So it doesn't go very fast normally. Normally, it's just sort of normal movement of water and heat. And this is called the neutral phase of the El Nino cycle. But about once a decade or so, more heat builds up and slows down the wind. So actually the wind is normally a little faster, and it pools, and the heat pools up around here. It's not being forced this way, eastward. It's just being not drained off to the west. And that long tongue of surface water gets warmer and warmer as there's kind of, think of it as like a doldrums conditions here where the wind is not moving, and it allows the water to heat up because the sun heats it every day, right? And so more and more heat builds up, and then it starts to spread out and move to North America. So this is the El Nino. And this heats water that then moves to the poles because it has to. It can't stay trapped. Then alternatively, when the winds pick up and move the heat out, we have cold water coming up from the bottom. So I can't show you the 3rd dimension, but as the heat moves this way, cold water comes up here from the depths, and then that gets moved over. And once the heat dissipates up north and south, then we have a big cold band. And that piles heat up here. You see, it's forcing the heat here to Southeast Asia to move to the poles over in the west of the Pacific Basin. And so all of this is a pump that moves water, and then this water, as it moves out, cold water goes back underneath and comes back up here to come around again. So it's a big cycle underneath. And this, when it's warm here, brings very wet conditions to Asia and Australia, and the El Nino brings very wet conditions to Central America and southern United States. And so here we see it from a satellite. It's not a satellite picture, it's a sensor for its data. But this is the cold tongue when most of the water has already moved here and it's coming back up and getting recycled. And then this is the El Nino condition, and you can see it starts to spread as soon as it builds up. Temperatures can really rise, not just in North America, but actually this affects the whole world. And this heat pump moves water toward the poles. This is like a release valve for heat that is built up that can't move by the wind, it moves by the water. So remember, I talked about this. It's always moving by the water. Heat is always moving by the water, not by the wind. And here it is going up through the Corrientes current. I forget the name of it. And then here it is coming straight up the Gulf of California. So I want to explain the data here. We have 3 phases, and they're interesting because the neutral phase is any of these back and forth phases that isn't very strong. If it isn't above this line, it's a neutral phase, and it's pretty common. There's plenty of low action here, and this is what we would call business as usual. This is since 1850, so we actually have a reasonable amount of data here. And in this neutral phase, spikes are low, and this is normal conditions. But then when the wind dies down and the heat builds, well, then when the wind picks up and moves the heat quickly, then we have the La Nina phase, which is cool in the United States. That's why we call it La Nina, because it's relative to the United States, but it's warm in Australia. And then the opposite, when the winds die down, we have these spikes. And so one thing to notice is that the La Nina and the neutral are more regular and more like offset. So this is kind of the normal rhythm, is from neutral to La Nina, neutral to La Nina. And then every 10-ish years, there's a spike. Very strong El Nino. 1878 was part of the worldwide heat wave and drought that killed 2 million people or more. Climate alarmists don't like to talk about that one because it wasn't caused by CO2. 1888 was very hot. The 1930s were hot. There's a lot of heat moving here. I'm sorry, I'm going to take that back. The 1930s were fairly cool in the Pacific Basin, especially in the 20s. There were some hot, but you know, one interesting thing is 1934 was the big hot year in the United States and Europe. And look, there isn't much action here. It's mostly cool. So that came from something else, and we'll see what else that was. But the 1940s were very hot. So that continued the hot wave that the other cycle started. And then you can see it's just stochastic. It's just, you know, kind of every 10 years. The big El Nino years of 73, 83, 98, about every 10 years. And then 2016 was huge. And you remember all the news cycle in 2016 was about the world ending again. Every time there's an El Nino, it's great for advertising sales for new media organizations. And this is the ENSO, the El Nino Southern Oscillation. And the way to think of it is that these are fairly normal, and these two occur about 3 out of every 5 years, and then the El Nino happens about every 7 to 15 years. So roughly every 10, 11 years. Enough heat builds up that it creates an El Nino event because the wind isn't moving it. And that moves the heat northward to get it out of the tropics. So the El Nino is really a heat. Here's like it's going along, the engine is going along, and then this is a release valve. Oh, there's just too much heat, and so we're going to release it here. Oh, there's too much heat built up, so then we'll release it. Whereas this is more or less normal operation, except for these long cold tongues, which is a very strong wind. Okay. And right now we're in a mild El Nino. We'll talk about that next week. Not a big El Nino. a mild El Nino right now. So we're in a warm phase right now. And that's probably going to end pretty soon. That was predicted, started last October. It's a winter phenomenon. So that's essentially probably over now. And then we'll probably go into a neutral phase after this. So at a larger scale, it looks like this. El Ninos are pretty variable. It's not consistent, but Javier's explanation is that the Pacific just occasionally builds up a lot of heat and then sends it north. And so this is like an average. Like there's more La Niñas here than El Niños. There's more El Niños here than La Niñas. A predominance of La Niñas, more El Niños. This is just kind of like adding up, if you kind of add up all this energy and see what the balance is, that's what this is. And then here's more La Niñas, more El Niños, and so forth. All right. And it's not really an oscillation. It's more like a just pressure release valve or a heat release valve. That's a better way to think of it. It's not trying to oscillate. It just has to move heat. Okay. If we had less heat coming in, there'd be fewer El Niños. Now that's the Pacific decadal oscillation. The El Nino is the event, and the Pacific decadal oscillation is the long-term description and the long-term trends. Okay. Then we have the Atlantic meridional overturning, and that's really part of the worldwide conveyor belt. It's a slow movement of water that pumps water up and north and down and south. And a full round trip of this takes thousands of years. But this up and down, I want to now stop share, and I want to show you on YouTube what's going on. So here I've typed in Atlantic meridional overturning circulation. Everybody can see my browser? Can you all see my browser?
Oh,
No.
Yeah.
Sorry. Good. Okay, hold on. I know what to do. I got to share screen again. Here, I know. I got it. Good. All right. Now you should see my screen. Right?
Yeah.
Yes. Okay, good. I have typed in Atlantic meridional overturning circulation. What are the results? Critical Atlantic Ocean circulation on the brink of collapse. Ocean current doomed. Overcurrent, turning current collapsing. That's nothing. Approaching a tipping point. Is it really shutting down? I don't know what that is. Okay, overturning circulation. This is a conversation with a guy who says he studies these currents to prevent collapse, and he wants to understand the collapse. This is all about collapse. Important for what will happen in the future. Collapse. Time to get ready. This guy is awful. This guy is really just an alarm machine. What is happening to the AMOC? Could it start a new ice age? That's just a cup experiment. Is this why weather is getting wilder? What will it do to the Earth? This is the polar vortex. It just goes on and on. Collapse, tipping point, collapse, shutting down, collapse, etc. This is actually Kurzgesagt, and it's all about collapse. Kurzgesagt is fully on board with explaining the collapse with nice graphics and so forth. So there really aren't any that explain the overturning, but I like this, and people liked it last week, so I'll show it now just because it's right here, and I'm going to narrate it. This is from University of Liverpool. This is a guy who set up a tank. This is a professor. Of course, he talks about CO2 at the end like he has to, but he's got a tank here of neutral water, and he's got a heat lamp over here. This is the equator. This is the North Pole. I'm going to go fast. Okay, he's going to put in ice cubes here. He's putting in blue ice cubes to cool the North Pole end. Here are the ice cubes, okay? And then, and then he's going to take a cup of hot water and pour it in This is the equator end. This is hot. And you see it goes down right away. That's just momentum going down. You see it's going to turn around and come back up because it's hot. So this is neutral water. It's going to fight that, and it's going to start moving back up. And now it starts, because of the upward pressure, it starts to take over the top. And here's the ice water coming down. And you can see visibly, this is a pump, right? As water comes up here, it creates a bit of a low pressure zone here that sucks the cold water across the bottom. It's pretty cool, actually. This is more of my favorite comparison of laminar flow versus chaotic. It's laminar flow, but it's of course chaotic on a micro scale. But this is sucking low pressure, sucking the temperature gradient across. And here, what's happening? The cold water is warming up because of the lamp. The cold water is getting warmer here and starting to come up and mix. This is only because of the lamp. And because it's touching the hot water, this area starts to warm up. And this, as he adds ice here, this continues the flow of ice falling down, of cold water. And what interesting thing happens here is that as this cold water goes down, nutrients like plankton and air bubbles go with it. And this feeds nutrients to the creatures thousands of feet below the surface that can't get it any other way. So this is actually a nutrient delivery system. And then, of course, he says it's sucking CO2 down, and then later it's going to come up and destroy the climate. And so, okay, so fine. That's kind of, you don't want to watch the last 2 minutes of any climate video. But that's a nice explanation of the way this stuff happens. So let's go back to where we were. Now, I'm going to get to this right now. Right here is the Gulf Stream. So now we're looking at the Gulf Stream. And the Gulf Stream is pretty much always warm. It's coming from the equator. It's also coming up, from below the ITC. It crosses the ITCZ because these currents are so strong, way under the water. This is pretty deep water, the deep warm current. And then it joins here. It gets hotter at the equator. This is all equator here. Gets warmer, and then it starts its journey here. And you see there's 3 different arms as it gets across the Atlantic. And these 3 arms can change in emphasis. So some years more heat goes to Southern Europe. Other years more heat goes to Iceland and Greenland. And other years more heat goes up to Norway and into the Fram Strait here and up into the Arctic. The changes in these currents are quite complex and very difficult to forecast. And yet it has a huge effect on the weather. We don't really know that much about the details and drivers here, but it does change on scale from year to year, decade to decade, and centennial scales because of this global conveyor belt pump. And up here in the very North Atlantic, there are some areas that are called the columns. And there are several of them. And they are about 15 kilometers in diameter. They're essentially round. And as ice melts in Greenland, as ice melts in the north, this is where the Titanic got sunk by an iceberg. As ice forms, the salt comes out. The icebergs are not salty. The icebergs are fresh water, and they drop their salt. The water drops its salt to form ice because it crystallizes out and the salt falls away. And that salt forms these heavy columns falling down 4,000 meters from essentially the surface down to 4 kilometers down. It's the world's largest waterfalls. There's several, and they're moving pretty fast because the salt is very heavy, and that drags down, first of all, salt. So there's a salt pump that brings more or less salty warm water up from the equator and then carries saltier water down. and back down south. And along with the plankton and the gas from the colder water absorbs more gas, right? From Henry's law, that cold water pulls CO2 and oxygen and nitrogen down. And so many fish can just swim around and live 5,000 meters below because they're getting this fresh flow of oxygenated water in this through these columns and then through that flow. So that's pretty cool that there's this whole sort of positive nutrient delivery system going all the way down here and keeping a whole ecosystem refreshed and nourished all the way down. And that's true also across the Southern Ocean. This all is saltier water that has more nutrients that many creatures thrive in. So this is the Gulf Stream, and the way to think of it is that it's pretty chaotic and hard to predict which way the warmer water will go. And that's why Europe's weather changes, really. Now, this is the Atlantic multi-decadal oscillation, the main driver. It's the thing that we were looking at, the AMOC. And this is from Javier's book showing a warm phase, but there isn't a good diagram of the multi-decadal oscillation. And so what we have is data. And this is the 65-year cycle right here. I've been promising this for weeks. We're in a warm phase right now. What a surprise. Just as magazines and media outlets finally figured out how to turn the weather into a solid moneymaker, and the marketing departments decided to boost it, we've been in a warm phase since 1998. You know, this is big El Nino, 1998. Remember, this is the Atlantic side, but 1998 was big. The El Nino, brought warm heat over into the Atlantic as well. That's how much heat that El Nino created. And that warm phase started because it's a cycle. And so this is our cycle, and this also reflects the news cycle of how crazy and hot it is. And there's just nothing to do with CO2 this way. It's been going on for millions and millions of years. It was this way melting. Look at all this. Back in this 1870s, the Atlantic was very warm. And in fact, there are newspaper reports. We read one of them 3 weeks ago or so, where we said Norway is melting and all the fish are doing whatever, and the icebergs are fewer and there's more ships are getting through. Remember, we read that, and then it got cold in the early 1900s. Then in 30s, it was very hot and we had the Dust Bowl, and this really affects worldwide weather temperatures. And in the 70s, they said cooling is coming and we're all going to die of freezing, because anytime there's a trend, the media will just take it and extrapolate forever. And so that's exactly what they're doing now. They're taking this trend and extrapolating forever. And so that's why we're doomed. The AMO, first of all, we're about 28 years into a 35, 33, whatever, 65 divided by 2, right? 32-ish, plus or minus several years, but we're 28 years in. So after how many years are we probably going to go back down? I mean, would you really bet against this? This is very likely to go back down within the next 4 to 6 years, and then it'll be predominantly cool. The AMO drives the ITCZ location, but the AMO and the ITCZ is complex. Remember, I talked to you about the ITCZ moving north and south. The ITCZ moves north and south on a longer time scale than this. The ITCZ moves north and south more or less on sort of 100+ year cycles. And so it moves a small amount every year. The ITCZ is not driving this. But most people say the AMO drives the ITCZ, especially at this time scale and possibly at a larger time scale. It's just stuff we don't have enough data on to know much. But you can see, I mean, if you're going to say, oh, what's driving our climate and what's the prediction? Well, the prediction is this is almost certainly going to go back down, right? It would be very hard to look at this and say, oh, this is obviously CO2. It isn't. CO2 did not start in 1996, or actually, this is the pause here until the big El Nino in 2016. So it'd be very, it's really a stretch to say, oh, look at what the CO2 is doing. Well, okay, but look at what we've been living through for, ever like this. So the AMO has really been going on for millions of years, and it's pretty much driven by temperature and salinity. So it just goes and goes. There's maybe a solar component to it, and we'll talk about that in a minute. But Javier sees the warm phases here also, similar to the Pacific, as a heat jam, causing heat to build up. And then it gets unblocked. And he says, that's what these spikes are, when heat builds up and it just gets unblocked by moving poleward. But we don't know the cause that well. We know it's been going on for a long time. I think the last time it shut down was over 12,000 years ago. And, we only have geological evidence for that. We don't know for sure. It's a puzzle to put together based on whatever evidence we can dig up. But shutting down, does not, how could you look at this and say it's going to shut down? It's going to be disrupted. There's a tipping point. Really? Seriously? So the whole shutdown thing is just an industry. It's just the climate industrial complex. This is business as usual. It just happens to be a moneymaker at the moment for the BBC. Gets more eyeballs. There's two more. This is the North Atlantic Oscillation, and it is atmospheric. It is not water driven. The positive mode is characterized by very high pressure in the mid-Atlantic. And in Europe, that leads to less robust westerly winds, causing cooler, drier conditions across northern Europe and milder, wetter conditions in southern Europe, which is down here, and in the Mediterranean. In North America, the eastern United States, during a positive mode, can experience more variable weather with potential for cold air outbreaks and snowy conditions extending farther south and east into places like Florida than usual. And then we have the negative mode, where there's less pressure differential. So pressure is more diffuse. We don't have the huge high pressure across the mid-Atlantic. And in Europe, during the negative mode, this leads to stronger westerly winds across and bringing milder, wetter weather to northern Europe and colder conditions to southern Europe and the Mediterranean. For the eastern US, a negative NAO brings cooler, wetter conditions to the southeastern, while the northeastern might have milder, wetter conditions. The last, and that's just an atmospheric effect, and it's just considered essentially part of the Atlantic meridional overturning. So that's not something to pay much attention to. Now then, we have the Indian Ocean dipole, which is interesting. It's driven a lot by the El Nino winds bringing and piling heat into Southeast Asia. And the dipole does not have a positive and negative mode. They call it positive and negative. So, but it's not more or less heat. It's just east and west heat. So in the negative phase, there's an extra heavy monsoon in eastern India and Indonesia, while it's extra dry on the east coast of Africa. In the positive phase, it's very dry in Southeast Asia and much warmer around Madagascar, with heavy rains and flooding possible in Ethiopia and the Saudi Peninsula. In places like Dubai, heavy flooding, I'm just going to drive this home, heavy flooding in the Saudi Peninsula and places like Dubai. So which phase do you expect we're in right now? Anybody, any guesses?
The one where it's on the left.
Positive. Heavy rain in the peninsula. And sure enough, we're in a monster heavy dipole, positive dipole right now. It's an extreme positive phase that they haven't seen since 1996. So you can see what drives flooding in these regions certainly isn't CO2. The last time it happened, it was the same. It's just that they've got more infrastructure that is not very well constructed for drainage. And so the pictures look worse, but the amount of rainfall is about the same. Of course, the rainfall can be more like in Abu Dhabi than in Dubai. I mean, there's no way to predict that. That's chaotic, right? So Dubai got hit, and Dubai has terrible drainage. So you get the dramatic pictures, and that gives the BBC and CNN a chance to say, well, it's obviously CO2. Humans are doing this. It's just such a stretch. It's just, you can only imagine that this is just about money and it's not about climate. This is heavily influenced by not only the Atlantic oscillation, but very much heavily influenced by the El Nino La Nina. And it's part of the overall heat pump we're about to see. So here is the composite. Now I want you to see that this is buildup. This is called the cumulative AMO and the cumulative PDO. And I won't go back, but remember all the spikes of the red spikes and the blue spikes? Well, this is adding them up. So here on balance, we have more El Ninos than La Ninas. Sorry, this is the AMO. We have more heat buildup for the AMO. It's here. It's, I think this is called positive, so we'll call it positive. So here we have more positive buildup, and then here it's more negative. And this is the 65-year cycle right here. Okay, this is 65 years. It builds up, it goes down. So think of it as 30-year cycles of more heat and less heat. And where are we now? 30 years of more heat on our way down toward pretty soon, as this slope goes down here for 30 years of less heat. This is the AMO, and then over on the El Nino side, here's 30 years of more El Ninos than La Ninas, 30 years of more La Ninas than El Ninos, 30 years of more El Ninos than La Ninas. And almost certainly we're about to go into 30 years of, and remember the El Ninos are release valve. So it happens, right? But overwhelmingly, statistically, more La Ninas for the next 30 years than El Ninos, which might help for ski seasons for the next. So if you've got young children, you teach them to ski, because skiing is probably going to be pretty good for the next 30 years. Skiing for the last 30 years has been horrible. And that is temperature. So once again, I'm the magician on stage pulling rabbits out of the hat to show that this is the smoking gun of CO2 not causing climate change.
Right.
Is this, and we're going to see less of the color red on all the maps, and the press is going to have to look for more extreme weather events and damage to property to tell the story of CO2 for the next 30 years. It's going to be harder for them. Now, this isn't very well correlated with sunspots, but sunspots, what drives this, right? Something is driving all this, right? So whatever's driving the AMO is probably very much what drives the PDO. These are very, very correlated in the Atlantic and the Pacific. Okay. And it's very likely that solar cycles do have something to do with it, but not one-to-one relationship. So the solar cycles don't come in a 65-year periodicity. So it's difficult to understand what is driving it. All we can say is we can describe it. How long has this 65-year cycle been going? We don't really know. Maybe thousands of years, but maybe, on the order of 10,000 years or so, what have you got? You've got precession, right? On a longer, you got obliquity driving the ice cycles. So maybe this doesn't hold for more than 1,000 years at a time, and maybe in 1,000 years it's something else. But right now, it's pretty hard to deny. This is probably driven by solar variability. It's possible, it's likely that solar activity does most of this. Think of it this way: more solar activity, less solar activity, more solar activity, less solar activity. That's probably what's happening, and we're going to talk about that later today. But it certainly can't be CO2.
David,
Judith, can you turn off your mic, maybe? Okay.
can I make a comment?
Yes, please.
65 years is equivalent to 6 solar cycles, roughly. So could it be that the solar cycle is just a harmonic of this 65-year-old cycle, 65-year cycle? I mean, I'm not saying it is, but I'm just saying it may be connected to the solar cycles.
I think coming up in another slide today, I'm going to show you the solar cycles overlaid on top of this.
All right, fine.
Yeah, so let's get to that.
Thanks.
Right. Somebody still has a mic open and background noise. Don't know who's the culprit. Okay, that looks like it's worked. All right. So look, this is kind of, hello, Javier, like, how more clear can I make this? What do what do you need? So we're going to go now to heat transport and the heat pump that I've been today is the culmination of about 5 weeks of buildup, right? This is the release valve. I'm finally paying off all of these things I have been promising. So meridional heat transport moves heat from the tropics to the poles. It has to. That's the Earth's job. And it's a 5-phase pump. 5 phases I'm going to show now. I'm going to use a Mercator projection, which has got 2 Greenlands and 2 South Americas and 2 East Coasts. So we'll just concentrate on, this area. And remember that the land and the atmosphere don't store heat. It can only build up in the oceans. At the equator, there's no wind to move heat north and south. It only goes west. And look, we just learned the wind does not really blow east. The wind either blows west or it stops blowing west. And then you get the El Nino. It doesn't reverse and blow east because that would destroy the Coriolis effect, right? So just sometimes it just takes a break and you get a buildup of heat here. But most of the time, the wind is moving westward. So during the La Nina phase in the Pacific and a similar phase in the Atlantic, heat builds up in the water. And then it needs to get moved to the poles. And so this stored heat has to get pumped out through the water. And it flows according to the location of the ITCZ at the time, not the equator doesn't matter. So we really should think of it as the ITCZ. Remember, the ITCZ is north in July and south in January, right? It's moving all the time. So this is an abstraction, okay? And this is phase 1, La Nina, where during La Nina, and we saw it in the satellite data, you get a lot of heat being transported up toward Japan. The Koryusho, I keep getting that wrong, but it's some big current that moves heat north. There's another one here. It turns out that here there are currents that will go north toward Saudi Arabia and currents that go south. And this is actually a pretty big one, and it sucks water all the way around Africa and then comes back up. So this is probably bigger than I'm showing here relatively. It's probably a mistake. And then that warm water just continues, gets heated up again, and it just continues its march across. We don't have anything kind of similar to that here in the Pacific, in the Atlantic. Sorry, we don't have anything similar to that in the Pacific but we do have this Africa effect in the Atlantic. And that's because not that much heat is being forced around the tip of South America, and the tip of South America is much colder than the tip of Africa. Probably also because the tip of Africa is far more north. The tip of South America is sticking into the Southern Ocean, and so it's very cold down there. So heat can't really come back up into the Atlantic, into the Pacific side from there. But this is phase one, where it starts to move heat north, and this is the El Nino phase, where a lot of heat is moving here. Okay, and kind of the normal amount of heat is moving in the Atlantic. Okay, but this is tremendous. So this has a worldwide effect. Now, moves heat through the ocean, and this is not sea surface temperature. Sea surface temperature does reflect things like the El Nino, but this is quite a bit of heat moving through hundreds of meters of water. Yes, it's at the surface because it's hot, but it's a lot of heat moving north. From 30 degrees, the interface between the warm ocean and the cooler air sucks the heat up and transfers the heat to the atmosphere. And 2/3 of the heat goes now via storms. And this is where all the storms start. They start at about 30 degrees north, and then they build up. And this is the tropical hurricane alley here. They all start right here at about 30 degrees, and they make their way, and they make landfall here in Florida and in the Caribbean. All of that stuff comes from the birthplace of storms, which is out in the middle of the ocean, where the heat meets the colder air and gets sucked up. It transfers because the heat goes from warmer to colder, and that's all happening here. Lots of heat transfer, and here it has to happen because a tremendous amount of energy moves over the Himalayas. In fact, a tremendous amount of energy moves over the Rockies and the United States and up into Canada, all storm driven. And many of those storms come from the Atlantic, and they will go right up the East Coast and stay on that track and move energy up this way, all over through the atmosphere. Maybe 1/3 of it comes up through the water here, mostly through the Gulf Stream. This is the main carrier of water heat, but still 2/3 of that is up in the storms and goes up all the way around in storms. And that's how you get so much snow dropping on top of Greenland, that there's 2 miles of ice here. It's all storm driven. From March to October, all this heat pours into the Arctic Circle, and it does the same in the southern, near Antarctica. And here in the north, it melts an area the size of ice, the size of the United States, by 2 meters thick, as we know, storing this heat like a battery until winter. So all summer long, we don't have the inversion. We just have melting ice storing heat. And each of these steps is like a ratchet during the year. There's seasons for all this stuff, right? There's seasons for the El Niños in December, right? This is in December, January, February. And then in spring and early summer, we have the big storms. And then during from June till September, we have melting ice. This is the heat pump. Okay, and each step is a ratchet that moves heat poleward, and every step of the way, whenever it melts the ice, it stores it, and then as soon as the Arctic Circle goes into darkness, the ice begins to refreeze. We get the inversion conditions. The polar vortex starts to spin up because the polar vortex is weak or doesn't exist during the summer. It's not there. And so that starts to spin up, and all of this energy starts to move out into space via the radiative. Remember, we've got condensation, evaporation, convection, and then finally radiation. And much of this up here is so cold that there is no evaporation. It's just radiation. It's just long wave infrared photons making their way to space to the emission height, and then boom, they're out, as we've seen. See how everything we've ever learned for 8 weeks is paying off right now in the heat pump? Isn't that like, is it like all coming together? It's like exploding in your brain, you know, because it's just gelled. It's just all the whole puzzle, the puzzle that Javier has on the cover has just come together, and you see the big picture right now. That the Earth is designed to pump heat the way the continents are now, and the way all the currents are right now is designed to pump that heat out through the Arctic Circle, through the polar vortex during winter when it's dark. Whoo!
Right.
Yeah. Does the IPCC talk about this? No. All right. Now, this whole cycle that I've just explained varies, and it's more active in some years than others. Okay. We're going to see that in a minute. In summer, when sea ice extent goes down, this is heat storage, energy storage in the heat sink of the Arctic Ocean. I can show you lots of graphs about this, but there's no reason to get it too complicated. The Arctic is not melting because of a heat wave. The Arctic is storing heat that came from Jakarta. Okay? And that's to be released starting in October. It's a show. It goes on every year, and then it comes back around again. So less Arctic ice in summer means more heat transport and more cooling. Less Arctic ice. If they say Arctic ice is not what it was a few years ago, great. Well, that's more cooling because the Earth has to do it. Nothing to do with CO2, and it's not a heat wave. You know, do journalists have time to figure this out? They don't, right? They will just take the simplest explanation anybody gives them. They call some scientist at Woods Hole and they say, what's up with all that ice? There's less ice in the Arctic. Oh, it's terrible. It's a heat wave. It's going to melt the Arctic. You can just take that trend and extrapolate it forever, and there'll be ice-free in summer. I wonder who said that. Who keeps predicting the Arctic will be ice-free in summer? Well, that's the people who don't understand, like Al Gore, who do not understand that ice melting in summer is storing heat for release in winter when it refreezes, and it will. There's more cooling because you're getting more heat out of the system. Make sense? You know, dear neighbors, you know, the people you meet and talk, are they going to believe this? No. Why? Because it's too much for them. It's too complicated for them. But here it is. I've shown this before. This is the series data showing 22 years of temperature change at ground level. And note how little the tropics change because they've got to get the heat out. And yet the boreal forest and Arctic see swings of up to 68 degrees centigrade. This is the heat pump right here. And actually, the heat has to go up here. Note also the huge amount of extra heat at the equator gets squeezed into smaller and smaller area as it goes to the poles. We've discussed that. The heat, that large amount of heat gets squeezed in, and that's why it gets radiated out so much, starting at 45 degrees. Much of it just comes out straight out the atmosphere up here because it's like a bulge of heat, and then the last remnants of it come out at the Arctic. So this kind of tells the story because this is the 30-degree line, but at the 45-degree line, this is kind of maximum heat exit over the atmosphere. And then much of it didn't get this is the concentration of it because this circle is very small. This is a much smaller area here. And that's why you get a lot more heat in the thermometers here because that heat is being concentrated toward the North Pole. Does that make sense? It's the same thing in the South Pole. Okay. Who understands this? Nobody. You know, even the IPCC, they've got people who understand this, but they don't talk about it. Every winter, NASA has satellites that see a tremendous amount of heat escape over the pole. Now, when I say a tremendous amount of heat, they can see it from a satellite. It's true, but we're talking about instead of minus 50 or minus 80 up here in the stratosphere, it's minus 40 or minus 30. So it's ridiculously cold from our point of view, but it's a huge amount of heat in joules that is coming up that they can measure. And if it's minus 40, they say, see, the poles are always cold. You know, it's just a heat wave coming over in the summer. No, that's releasing all that heat, refreezing all the ice. Nothing to do with CO2. This is normal operation. And yes, there's variants of it. So I am now going to take less than 2 minutes to talk about the winter gatekeeper hypothesis, which is Javier's invention of how this works. And it's very complex. I'm taking out 99% of the detail right now, and I'm just going to give you like 3 slides. Okay. You don't have to, you can go use the bathroom if you're not, you know, this is climate geek stuff. Okay. Simply says, this is the AMO with weak transport, and this is the negative AMO with strong transport. Okay. And during winters with higher sunspots, there's a stronger AMO, which results in weaker transport and less heat escapes. So there's more warming when there's a higher AMO. And we see that. That's the red in the graph. Okay. And that, he says, has a lot to do with sunspots, as we were discussing. And then during winters with fewer sunspots, there's a weaker vortex, a negative AMO, strong transport, and for the North Pole, this leads to a warm Arctic in summer and cooler overall global temperatures because it's sucking heat out more. So there's this gate during winter where if it opens, this is the gatekeeper hypothesis, that more heat is allowed to leave. More heat can escape during this negative AMO phase. And of course, that's why it's blue at that time. That's why temperatures go down at that time, because it allows more heat to escape. Now, he really correlates it with sunspots. And this is his hypothesis. He says it remains to be seen because here we've got a sunspot diagram here, and that this corresponds to the AMO is doing what it does, but when the sunspots are low, it allows the heat. So we kind of hit this concept of windows of opportunity before, where there's a window of opportunity for a climatic event, and and for example, a glaciation, right? They don't always happen. We've seen that in lesson 2. It doesn't always happen. There's no perfect correlation with, say, obliquity, but obliquity opens a window to allow a glaciation or an interglacial. And it's the same here, that the sunspots open a window, a gate during which the wintertime heat escape there can be more heat escape. And then other times, because of higher sunspot activity, the gate is more closed. So that modulates the amount of heat that can escape, and that gives essentially the AMO. That's his hypothesis. Or that gives essentially the world, the 65-year cycle of world temperatures. And that might be true, and it's probably at least to a large degree true. But there's, it will take us, we might need a couple hundred years more data to show that it's a very strong correlation with sunspots, because we don't have all the data we need. Does that make sense? I mean, I'm trying to keep the hardest material in a very complex book as simple as I can. And so if you basically understand that, you're doing great. Good? There are a million questions here. So, how does this really work? I don't know. It actually has to do with the the length of day and the rotational momentum of the earth and a whole bunch of stadium waves, gravity waves, all kinds of things that I don't understand, but this is the basic concept. All right, now we've got our final technical section, and that's albedo, and it's not that technical. So I'm happy to, I just want to make sure everybody understands this. Is there any questions about this whole heat pump? 5-phase heat pump, because that's the main thing to remember here. Anything about that anybody wants to ask?
Hey, David, can we consider the term solar activity to be a synonym for sunspot activity?
Yeah, well, I think.
I hear those terms, and it seems like they're used interchangeably, but I'm not sure that I know the definitions of them well enough to say they're the same or not.
Yes, and I'll tell you why. Yes, I'll tell you why, because you don't use that term solar activity on a long scale like eccentricity, right? That's a different thing, right? That's insolation, right? That's being farther away, right? And you don't hear it with albedo, which is where we're going next, because with albedo, you don't need a change in solar activity at all. You need a change in reflectivity, right? So my answer to your question is yes.
Okay, thanks.
Yeah. So here's the slide I promised somebody about the sunspots. We'll look at this. This is from the graph that we saw in day 2. And this again is, part of why Javier, proposes that the sunspots open windows of opportunity. And this black is temperature. It's very tricky to give us temperatures of the last 100 years because this is all hand readings of thermometers here, thousands and thousands of thermometers versus satellite data that isn't even measuring the same thing. This is a bulk bottom 2,000 feet of the atmosphere in the troposphere temperature reading from satellites. And this is ground level thermometers. But so this is our temperature, because, you see all these temperature graphs and they do this, okay? Like from Berkeley, Earth, and from Hadcrut and all these in NASA, you see these temperatures that show low temperatures in the 30s and high temperatures from the 80s on. And that's all cooked. That's all cooked data. So if you want to not cook the data and just go with more or less raw temperatures, you see very hot 30s that are essentially within margin of error of the same temperatures we've had up until 2022. And then I'm going to explain that next week, why it's particularly hotter in the last 2 years. And here are the sunspots. And so, yeah, it's hard to say that this is driving this. That's pretty hard, right? I mean, this is a low sunspot time. And this is pretty accurate. So this is a little more, these are cycles 25, 24, 23, 22, 21, 20, cycle 19, cycle 18. It certainly has something to do with it, especially maybe when it's low. Here's a low spot. And then it's on the way down. So we're on the way down now. And then pretty soon we'll be going back up on an 11-ish year. You can see it's not very regular. It's kind of regular. I don't like the word 11 years, but 10 to 15 years-ish, sure. Cycle. And there's still missing pieces to this. It's obviously not just driving. Okay. And so one of those missing pieces is albedo. So this is exactly what you just said, Dan. This is solar activity. Okay. But it's obvious that it's not the 100%, correlation driver. Okay. So one of the missing pieces is albedo. Albedo is what? Who's got, let's get into it. Who can tell me the definition of albedo?
Reflection.
From what? What's reflecting?
can't remember if it's high frequency, where it's the heat from the sun reflecting off of bright surfaces like ice and snow.
Anybody else? Okay, we got ice, we got snow. What else is reflecting?
Land and dust.
What?
Land and dust.
Land and dust. That's the 4 categories right there. Heat, ice, land, dust, and clouds.
Clouds. Oh, sorry.
Clouds, right? There's a tiny bit of reflectivity from the ozone layer, but it's not something we can see. It's not something you would really see from space. It's mostly clouds and snow. Okay. Then comes dust and water. Water is, I'm sort of surprised. I thought that water would be more reflective, especially, when the sun is low, if this is where the sun is all the time, right? And over here, it's pretty shiny. You need polarized glasses if the sun is down low, right? There's a lot of shininess you would think goes off to space. And it turns out, and I'm not sure why, because intuitively I would think that any water, any sunlight coming around here would go, and it probably does, but it's just not the main part of albedo, which is clouds right in here. And I guess ice is much shinier than water. And so here's the puzzle. Here's the equator. The Earth's northern hemisphere has exactly the same albedo as the southern hemisphere, even though they're vastly different. And clouds have a lot to do with where's the land and where's the water, right? And clouds cover between, about 20% and 80% of the surface of the Earth at any one time. A lot of the time, it's about 60% of the surface of the Earth is covered by clouds. And yet, these 2 hemispheres are equal in albedo to a very close, small degree. It's much less than 1%, and nobody knows why. Obviously, clouds have a lot to do with it. No one has put that particular puzzle together and been able to predict. And it's probably important for the planet in some way, but it's an interesting, if you're taking a science class or a climate class, there's this kind of interesting conundrum that the 2 hemispheres have equal albedo. According to Javier, a 1% change in albedo has a radiative effect of 3.4 watts per meter squared, almost equivalent to a full doubling of CO2. Now, there is a logical fallacy in this calculation that I've mentioned before. It is only for climate geeks. When they talk about a doubling of CO2, climate sensitivity, we went over this, ECS, leads to 3.4 watts per square meter. It's about this, it's the same. It's not true. There's a nuance here, and that is 3.4 watts per square meter of more incoming solar radiation is all high frequency, right? And yet, if you doubled CO2, you'd add outgoing long wave, low frequency, long wave, low energy to the equation. And so it's not the same, because 3.4 watts per meter squared in high frequency incoming can penetrate the ocean, and that equivalent in downwelling infrared radiation can't penetrate the ocean. So it doesn't have anywhere near the same. These 2 things are not equivalent, and it's just a big fallacy in the logic of the IPCC. Andy May talks about this all the time. Just there is no climate sensitivity if it can't heat the oceans. So how about climate has 0 sensitivity to CO2? How about that? Doesn't matter how much. You could double it 10 times. It still doesn't drive any heat into the oceans, and so it doesn't affect our climate. It's just wishful thinking on the part of catastrophists who think everything is going to hell. Anyway, sorry. A 1% change in albedo has a big effect on climate. Not this silly nonsense effect, but say 3.4 watts per meter squared. Forget this part. 3.4 watts per meter squared of incoming sunlight. That's a big effect. That's big. That's what the clouds, if the clouds change that much, big effect. And here we see it. Total albedo since 1981 has gone from 29.6. Remember I said we're at 29%? Well, we're actually at 28.8%, so close enough, but we've gone down from 29.6, so almost a full percentage. And guess what? That's roughly 3.4 watts per meter squared. It's a lot. So it goes down about 1 percentage point in the last 30 years. And that's probably happened over and over and over thousands of times. We're probably about to go back up in albedo. It's just that we haven't been measuring albedo for hundreds of years. So we can't overlay that on the AMO graph that I showed before. We don't have the data. But it's gone down for 30 years. What time period does that coincide with? The same time period in which temperatures have been going up for 30 years. And this is cloud percentage going down and temperature percentage going up. It's very squiggly. So this is just on a rough, every on a composite basis. And here we see solar radiation reaching the Earth has increased on a watts per meter square basis by a couple watts, almost 2 watts per meter squared since 2000. This is since 2000. So for the last 30 years, it's probably on the order of about 3 watts per meter squared. Well, that is enough to drive temperatures up the way we have seen. That's all you need to produce the temperatures we've seen and to produce that AMO correlation that we've seen. All you need is variance in albedo of 1% up and down. And so we can say if temperatures are going up on the surface, then the Earth is receiving more solar energy. Now, if it's CO2, and the CO2, if the energy from the sun is not changing because let's say albedo is the same, that's the hypothesis, then it's got to be CO2. And CO2 then is trapping more, there's more trapping. If there's more trapping solar energy on the ground, that means that there should be a slight decrease of outgoing long wave radiation at the top of the atmosphere. That's the only way you can trap heat in the bottom for having warmer temperatures is to have slightly cooler temperatures high up in the stratosphere, but that's not what we actually see. It's predicted, but it's not true. Satellites measure the opposite. They measure a slight increase in outgoing radiation. And that would be consistent with more sunlight hitting the Earth and bouncing away than greenhouse trapping heat. Does everybody understand what I just said? Okay, if it's CO2, we should see less outgoing long wave radiation at the top of the atmosphere. We don't. We see more outgoing long wave radiation at the top of the atmosphere. That means there must be more sunlight coming in and then being reflected back out. Now I'm going to drill this home. This is a recent paper. As in other recent studies, we find that by far the largest contribution to the increasing rate of the change of Earth's energy imbalance is from an increase in net absorption of solar energy by the planet that has happened over the last 2 decades, due to reductions in the amount of solar radiation reflected, a reduction of solar radiation reflected to space. No CO2. I don't have to convince you guys. I'm just like hammering nails in the coffin all day long. I'm out of, I got plenty more nails. It's just, I think the coffin is closed. But this is a paper from NASA. And a lot of people think NASA is this, you go to climate.gov. Who is that? That's NASA. Climate.gov is NASA propaganda, government propaganda. And on climate.gov, they don't have a link to this paper published in 2020. A NASA paper that NASA employees don't know about and don't want to know about. This is studying the Earth from a new satellite at the Lagrange point between the Earth and Sun. What's a Lagrange point? Anybody? Lagrange point. Come on. Come on, climate scientists.
Well, the Lagrange point is 2 points between the Earth and the Moon, which the French mathematician, using Newton's laws of gravity, worked out, so that you can put vehicles into the Lagrange points and they'll stay there because it's there's no further increased pull on them while they're in the Lagrange point. It all balances out.
Yes, it's exactly the point at which the gravitational pull of the Earth and of the Sun are equal. All right. Now it turns out there's 4, and they're actually rings of these. So there are rings of Lagrange points that go out away from the Earth. If the Sun is here, the Sun is over here and the Earth is here. There are rings of Lagrange points at different places, and there's one here between the Sun and the Earth. I forget what it is. I think it's a little farther than the Moon. I think it's 1 million miles away. The Moon is 250,000 miles. I think it's about 1 million miles away or something. There's another one on the opposite side that I believe is more than 1 million miles away. And what's out there at the other side, the Lagrange point at that side? What's out there? Anybody?
Is it the big planets like Jupiter?
No, Jupiter's many millions of miles away. The other Lagrange point where it's equal, where something can stay without, it won't wander, it'll stay right there. This is a solitary point. If you put something out there, it's not going to move. It's just going to be dragged around the Sun by the Earth, and it'll always stay there because it's equidistant gravitationally between the gravitational pull from the Sun and the Earth are the same.
Moon.
What's the other thing over here on the other one?
The moon.
Huh?
The moon.
No. The moon's, the moon's going around.
Oh, okay.
It's about 1 million miles or maybe a little more. There's some piece of.
Is it just in orbit? It's centripetal force. It's just orbiting the Sun.
No. There's a Lagrange point over here on the opposite side of the Sun, where if you put something there, it's going to stay with the Earth going around the Sun.
Okay.
What is it? There's a piece of equipment out there. What is it?
Planetex?
It's the Webb telescope.
Oh.
The Webb telescope is there, and there's
Wow.
Yeah, not only the Webb is there, but it's not only just a Lagrange point, but around the Lagrange point, there is a circle that is itself a Lagrange point. And they've got 2 satellites there now, 2 telescopes there now. I forget the name of the other one. And they're planning 2 more. So this is a big area. These are big distances, like 100,000 miles between them, but it's a big circular Lagrange point they can create where the Earth will just drag that around with it and it will stay there and it doesn't wander off. Pretty cool. Then there's more of those out on the flanks of the Earth. So there are actually quite a few Lagrange points. And if you're interested, there are videos that show this better than I can. All right, so this is a new satellite, the Mera 2 satellite. And thank goodness Al Gore, in 1998, there was so much heat from the El Nino that he got funding for this new satellite. And thanks to his funding, and because we have that satellite data, his goal was to then use that to look back on Earth and measure how badly the Earth was being destroyed by humans. And thank goodness for that satellite, because we can now prove that it isn't happening. And I want to read you their conclusions using their data. Our research supports the idea that clouds and albedo, which ultimately determine the incoming shortwave radiation, are variables of the utmost importance for current climate change, in agreement with previous research about the changes in stratocumulus or energy imbalance in the last 4 decades. No mention of CO2 in this paper. And that's from NASA. These are essentially, what is albedo? Is it a cause or an effect? Sorry, I didn't mean to have that there. What causes albedo to change? As far as I can tell, we don't really know, and there might be some good papers on this. I'm not as up to date as I should be. Albedo could be a cause, or it can be effect, or it's a complex dance of many things, and it's partly both. But more solar energy is getting to the surface of the Earth. That is what has caused our warming. And as we go to a cool phase of the AMO next, that albedo is probably going to change. And we're going to learn a lot in the next 50 years about albedo, because we can measure it now. And I predict we will get the same effect in the future. And I predict we will have much less albedo. But albedo could be the byproduct and not the driver. We don't know. That's 3 modules today. You've gotten through all the heavy lifting that has been 1,000 times more than what you bargained for. But I think you understood it today. Is that right? Can you say that? Pretty much. Because I've trained you, because I've conditioned you, I've bludgeoned you into all the pieces that you need to put that puzzle together. So I hope you can feel a bit of sense of accomplishment and relief that it's over, more or less. And there are many parts. And on the first week of June, you're going to present your parts that you find interesting. But that's the big picture. And I hope that whole puzzle, 1% of what I've just said in the last 8 weeks has formed a model in your mind that you can at least, if other people don't believe you, that's okay. At least you can feel like you have a grasp of it. Okay, comments? Charles, as always, is going to now say something intelligent. Where did Charles go? He disappeared. Oh my gosh, we scared him away.
Can I confirm something?
Yeah.
Hello?
Sure.
Hello?
Yeah.
Oh yeah, okay. So the Atlantic meridional oscillation and its cousin in the Pacific, but we looked at the graphs, and the temperature goes up and down in 65 years cycle. But this is clearly not related to CO2 because it happens during the industrial period. Have I understood that clearly?
And the Pacific is really not the same as the AMO at all. The AMO really is pretty regular, 65. You got to think of the Pacific oscillation as a pretty normal oscillation between neutral and La Nina, and then occasional El Ninos that slam heat up mostly to Mexico and the United States because it has to release. And so it's not as much of a regular thing. It's more intermittent.
Thank you.
Those are more like one out of every 10-ish years on average, whereas the main business as usual between La Nina and neutral is kind of 3 out of every 5 years back and forth.
Mm-hmm.
Exact year in the 1878, and I've got an article I've written on that is right here. I think Dan has read it. The Great Famine of 2078. Does anybody remember that one?
Uh-huh.
The Great Famine of the 21st century, and that's kind of a trick article to get you to realize that what you think is true is not true. 2 million people died at least. And in Wikipedia, it says that about 10 million people died. I don't think that's true. But it was a horrendous event. And it was worldwide. It was a famine and a drought and just a heat wave. And there's a lot of really interesting stuff about the British Raj, and the terrible way they were governing India caused 1 million people to die in India just because they were keeping the average Indian person couldn't get any food because the British were controlling everything.
Oh.
Really, really horrible regime.
Can I
Nasty.
say something? Can I say something about that?
Yes.
Famine is endemic to pre-modern economies. That's how it works. We had famines here in the UK up till about 1650, I think.
Right.
So everyone gets slated. Poor old Churchill gets slated for and the Raj for those famines in Bengal. That is how pre-modern economies work, because agricultural productivity is so low.
True.
And the people who went up there, they invented because everyone was starving, so they had to invent this very thin gruel. Because if you give rich food to starving people, they die. And that rich food, that discovery they took with them, they took it to the terrible places I can't even name in Germany in 1945, and they said, "We know how to deal with this. We know how to deal with this," because they tried their best in Bengal.
Yeah, they didn't actually. That's not true. The British had taken the stuff in Bengal that were normally stored in the years of plenty, so that in the years when there wasn't so much, people could rely on stored food. But the British and the East India Company and the British behaved very badly in India, and they took the food that Bengalis had stored to use for their troops, which meant that when they had a bad year, there wasn't any food for them to fall back on, which had happened in previous generations. So I mean, I'm British, but I think that we have to look at our history and realize that what we've done in the past has not been exemplary.
Thank you, Judith. In fact, Corin, if you read that,
but the point remains.
if you read this document I put down, you'll see that I have links to very much of that, and to some papers and to some videos showing how really, really awful the British Raj was. But you're also right, Corin, in the sense that there was a tremendous amount of variability, and a lot of these famine events couldn't be prevented, and they really did. That really was part of normal life. Go ahead, Corin.
Oh, yeah, if I could ask something else. I mean, I get that thank you for the stuff about the heat pump, which I barely understand.
Where's your camera? You're off.
Okay, I have no idea how to put it back on again. Okay, so I get what you were saying about the heat pump and the effect on Arctic sea ice on an annual basis. And I've seen how they start the graphs in 1979 at the high point of the cyclical nature of Arctic sea ice, and then we look at it now and it's the lowest point and it's going back up. But I didn't get how the heat pump influences the level of ice in longer than annual periods.
Because of the winter gatekeeper effect, because some winter more heat escapes and some winters it doesn't.
Yeah.
And during the AMO high, it doesn't, and during the AMO low, it does.
Okay.
And that's how you get the global temperature cycling at the same correlation as the AMO.
Okay. Thank you.
Yeah, and that is Javier's contribution to climate science. Aside from debunking everything else, he explains why the PDO does that. Now, we still don't get all the drivers, because I'm not willing to believe that albedo is a driver. And he says that too. Sunspots can drive because they can change the amount of incoming solar radiation. Okay, that's a driver. Okay, it's probably true that albedo is more of a passenger. It's more of an artifact of, if temperatures get warmer, what's going to happen? More clouds, right? And as temperatures get cooler and we go into that trough of the AMO, fewer clouds, right? So the albedo could easily be a reflect, and again, we don't have enough data, so we don't know, but it could be that it's just showing you how much less heat we have in the oceans, or how much more heat we have in the oceans, and that's driving albedo. But there are, you got to keep in mind, there are knock-on effects. There are circular, there's feedback. So you get more clouds, you get lower temperatures. You get fewer clouds, you get more temperatures, but it's probably more driven by sunspots plus, for example, time lags in the system. Sunspots add energy and take away energy, but there can be time lags in the system that prevent it from being one-to-one correlation. Does that make sense? So that it's
Okay.
probably something more like that is the driver.
Okay, thank you.
Sure. You can tell this is hard and we don't have enough data to be very conclusive yet. About the best we can do right now is more or less negate a bunch of stupid theories and just trying to keep knockoffs theories that don't make sense and trying to see what's left. Stuart, yeah.
Is the figure of 0.29 for albedo, is that an annual average? Because the clouds are some days are 20%, some days are 80%, and it's patchy all over the planet as you look at it. So is the 0.29 an average, a long-term average?
Of course, and it varies by latitude as well. So, and the same amount of cloudiness has different albedo, whether it's a stratocumulus or a stratospheric, whatever other cloud. Depends on the type of cloud. You can have the same amount of water in the atmosphere, but one is much whiter and reflects more heat. Also, the stratocumulus clouds, which are the anvil clouds for storms, they trap a lot of outgoing heat. So it's really complex. There are people who do study this, but it's going to be, latitude dependent and dependent on you could have a lot of water vapor in the air that's not forming clouds. And then there's no albedo change. So it varies a lot. Does it vary over, say, 5 and 10 year time scales? And that's what we're trying to understand here.
So is the momentary albedo varying? Does it go from 0.1 to 0.3 or to 0.4 with an average of 0.29 over a year or over a number of years?
It's an average. So,
Right.
yeah. So the average moves over time. If the albedo changes on a monthly basis, that's not much of a climate driver. But if it changes by 1% over 20 years, that's a big climate driver.
Yeah.
David, are you familiar with any, there was something I saw, I'm thinking it's maybe 10, 15 years ago, some documentary. One of the features was also related to the solar activity was cosmic rays change and how that affects cloud formation. Is that something that you're figuring we're going to cover, or is that kind of
we did. No,
Oh,
we
okay.
covered that because that's galactic. Remember the spiral
Okay.
arms, moving through the spiral arms. So there's a 50 million year cycle, and then there's I forget how many million year cycle for the going up and down through the galactic plane. How many million years is that?
I don't know but what I was referring to, it had to do more with just the sun, how much cosmic radiation was coming from the sun to Earth, however much that varied impacted cloud formation.
It doesn't really, it's almost about the same. What differs is the galactic, is all the
Okay.
cosmic rays are coming from mostly supernovas. Right. And so those can come from any direction, and they come for, hundreds of millions of years or whatever until they get here, and then they can have a big effect. And there are some articles and people talking about cosmic rays on the order of 10 and 100 years, and I don't know anything about it.
Okay.
I feel like it's probably not cyclical, because the arms of the galaxy and bobbing up and down through the plane of the galaxy, that is cyclical. And we see that. I've shown you that in the data already. We see these big trends over millions of years. It's not eccentricity. Eccentricity is 100,000 years and then 400,000 years. That's eccentricity. If you're doing something over millions of years, that's galactic. And it's a regular thing having to do with the sun making its trip around the center of the galaxy. Anything else cosmic is more stochastic. It's more, depending on what's just coming from which direction, at the time.
Okay.
So it's not going to have a trend. That's what I'm saying. I think.
Thanks.
Then the other one is magnetic. Oh, the magnetic pole is going to flip or something. There's this magnetic. Well, the magnetic pole flips very irregularly. It's a chaotic system that we cannot predict. And sometimes it flips very quickly, and sometimes it takes many thousands of years to flip. And so I just don't see how that's going to get into the data. And it might have something to do with it, but I tend to ignore it because I don't see trends that I could, use to make any kind of predictions. Like whatever it is, it's going to happen however it happens. And I don't see it as a particularly big driver of anything, but it may be. People talk about it. I think it's probably noise.
Okay, thank you.
Yeah. Anybody else? Anything else, anybody? We're kind of done with the heavy lifting here after 8 weeks
My goodness.
of hard slogging. Anything that was kind of like, it's kind of good to bring up these questions, Dan, because, it was like 6 weeks ago, we talked about the galactic arm, stuff. And then I reinforced it again a couple weeks ago, but it's keeping all this stuff in your head is very difficult. It's really hard. People look, volcanoes, volcanic activity. Well, all right, but what's causing more volcanic activity in the last 30 years? Really? Something? I mean, so volcanic activity is one of these noise things that if you look at it, read the papers, it's tiny. It's tiny. I read a paper where they know very well along the trench in the middle of the Atlantic Ocean where these vents are that are venting water at thousands of degrees that's coming off, or I don't know, hundreds and hundreds, 600-700 degrees centigrade, I think, from the center of the earth. And they've got these vents and they've got these special bacteria that can survive there and all that stuff. And they dragged a sensor, I forget, like 2,000 meters down along right above all of those vents for, I don't know, a couple of days or weeks. And they didn't measure a thing. They didn't see any change in heat because it's tiny and it diffuses in the giant oceans. So it might be 600 degrees Celsius, but it's just not enough to make much of a difference. You can imagine, though, as a plate like India smashes into, Asia, that could generate a lot more earthquakes. That could generate a lot more CO2. You know what it probably has something to do with? The shape of the continents and the water flows and the momentum of the earth, the timing of how long a year is or how long a day is, because that's a tremendous amount of disturbance. It's a lot of mass. And so you could disturb the climate by changing the water currents, but putting more CO2 in the air isn't going to do it.
No.
So I don't, the whole argument about volcanoes, number one, putting more CO2 into the air. Well, volcanoes year to year are always putting about the same amount of CO2 into the air. And so, yeah, some years there's more and some years there's less, but there's no trend there. And then the other one is direct heat, which is really nothing. It's really just noise. There's no amount of direct heat and again, there's no trend. It's the same amount of direct heat for the last million years. So not much of a signal there with things like magnetism and volcanoes. I just tend to not pay attention to those conversations. For example, let me rant on about that. There's 3 parts to Antarctica. There's the Eastern Peninsula or the Eastern Plateau, which, as we've seen, is the coldest desert on Earth and is not going anywhere, doesn't melt, doesn't have any icebergs, doesn't have any, not affected by anything really. And we saw the trend in my video last week. It's flat, okay? And then there's Western Peninsula, which is warm and variable. And then there's the whole Well, then there's West Antarctica, which is much lower down. Sorry, it's where the McMurdo station is, I believe, and it's much lower elevation. So it's down, under 4,000 feet elevation. And then there's the peninsula, which is one of the most volcanic areas in the world. There's 138 volcanoes active in that peninsula of Antarctica, some of which go pretty far north. And if you want to measure extreme temperatures in Antarctica, and Antarctica is melting, you go to the very farthest north one. There's one volcano, and temperatures there at that weather station, what do you know? They are higher than the rest of it. And based on that one station, I'm telling you, Antarctica sets a new temperature record. New record. Warmest ever. Yeah, sure. That one station went from an average of, 8 degrees centigrade to 9 degrees centigrade, or I don't know what, or the new maximum temperature, you know what it was? It was 28 degrees centigrade. Well, sure it was one day. The thing to understand about like hottest thing ever, let me go through that real quick. Hottest anything ever, like on the first Olympics, the first day of the modern Olympics, how many Olympic records were set? All of them. Every single one was a new Olympic record. 4 years later, how many new Olympic records were set?
2.
90% of the records fell 4 years later because it's just not that hard for one person to do a little better than 4 years ago. They're just getting the whole Olympic machine going, right? So 12 and 16 and 20 and 24 years later, a lot of records fell. Why? Because that's what records do when you just start them recently. Right? So we talk about the hottest year ever. Since when? Since we've been measuring them, I don't know, 40, 80 years ago? Okay, well, sure. You're going to have a lot of new records. You're going to have a lot of low records set. It's the same game on the low side. Guess who doesn't talk about that? Right? A lot of new low temperature in Siberia, new low temperature in Phoenix, new low temperature in Oaxaca, whatever. That doesn't make the news. Because it's all pressure systems. Sorry.
It's this kind of a fantasy of power. It's like kind of people think we have so much influence and I'm so important. Myself, I can actually change the temperature and I can eat any amount of guilt and shame that I want. I've been there. It's not good. And we have a service here, I have sinned in thought and word and deed, and people have to say it every Sunday. And it's hard work. So thank you very much for chipping away at this.
Go to the BBC website and type in new temperature record. It's all going to be positive.
Yep.
Since when? Well, since we started keeping records. Well, that's nothing. You must have new temperature records set every single week almost somewhere. Because we don't have 1,000 years of temperature records. We have maybe 100 in most or less. Maybe since about the 1950s, we've really been taking quite a few temperature readings. All right, so every week there's a new high. There has to be. You could practically build a model on this and predict it somewhere. How many new temperature records you're going to see over the next 20 years. You'll see plenty, and they'll both be about as many high as low. You
can kind of see it if you see a graph of like the highest temperature record and lowest temperature record for every day on the calendar. And it makes this sort of an arc kind of a thing through the seasons. But you can look at, say, June 15th, the highest temperature in Rochester, Minnesota, where I live. The next day, the highest temperature might be 5 degrees cooler. Well, there's nothing inherently different about the weather pattern over one day. So, there's a certain amount of variability when you only have that many observations. And if you had 1 million observations, you'd probably have a lot smoother curve. all, you know, the highest temperatures would follow a real nice smooth curve. But it's this comes to where your discussion earlier about you want to talk to us about some of the statistical reasoning. Because people who don't understand statistics are the bane of our society. You know, it's like
Easy to be fooled. Yeah, if you think about those margin of the highest temperature record anywhere ever, whatever gets announced, it's smaller and smaller and smaller. It's just like the running times, right? The running record for any distance gets smaller and smaller and smaller because it has to. Because we're measuring a lot more. We've got a lot more tries at it. Right? We're just making
Right.
very marginal incremental changes to anything. And that's true with temperature too. So when they say it's a new record, boy, you really have to torture the data to get that tiny 0.1%, you know, out of it. Right?
That's a detailed question.
Yeah.
In the original, in the first slide, you were showing the currents going around the world.
Yeah.
At the south side of the Earth, there's a cold current and a hot current, almost side by side, and I don't know why, because
Yeah,
I would expect.
This is the Southern Ocean. The
Yeah, Southern Ocean
is ridiculously cold, and it's always going, and this is interesting, it's always going the opposite way of the Coriolis effect. Why? Because so much water is going west at the equator that this is coming back around. So it's
Okay.
always going east, right? But it's a ring of water. It's funny, you know, the North Pole is a hole of 2 miles of deep water ringed by land. And Antarctica is a plug of 2 miles high of Arctic plateau of land with 2 more miles of ice built up on it, ringed by water. These things could not be more opposite. And this Southern Ocean stays very cold. It's self-insulating. And so it's the only way to move air across that thing, or move heat across that thing, is through the air. Just like Javier talks about. You've got warm air coming across Antarctica and releasing, and guess what? Guess what? When I say warm air coming down across Antarctica and releasing, I'm talking about -40 instead of -70. That's warm air. That's heat. That's heat. That's a tremendous amount of heat coming from the equator down here and going to -40 and releasing through long wave radiation, through photons. Instead of, if it weren't there, it'd be -70 or -80. I mean, it's, you know, we're talking about the stratosphere up here. It's very, very cold. Okay. So when you talk about, they talk about some small amount of heat gives us a tipping point. You know what that is about? That's about, okay, sure, up here where the temperature is often near 0 degrees centigrade, you get a little bit 1 degree more, you could have a bit of an influence on the amount of ice. So we can measure a little bit less ice because of a 1 degree change. That's the 2,200 joules or 330 joules needed to freeze ice, right? So that can affect the amount of ice. Down here, a 1 degree change from -50, -80, it doesn't do a thing. It's noise, right? So here you've got something to report because you can show those ice maps of how dire it is, you know? And down here, it's like, are you kidding me? This is not going anywhere.
I get that, but it was about the deep water currents in the Southern Ocean. There's a cold one and a hot one. I mean, obviously they're huge distances on a map of the globe, but they look fairly close.
They are, because we get warm water coming down from the equator, mixing with that. Let me just see if I can do it. I'll just do it. The people can leave if you do. Of course, you can leave if you want. Here, right? See that?
Yep.
All right, so this is pretty understood that this is all deep cold water coming down, right? And then here it mixes with this hot layer coming through, and this hot layer is coming through is the a lot of this hot. Remember this circle is very small, right? This is not very big. This is tiny, right? It's down in here. Right, so this projection magnifies it. It's really a small circle, and most of this heat is coming in from the equatorial Pacific and then going around, and pretty soon it gets cold. So this is not really as red as it looks. It gets cold. This is cooling here. This is not coming the other way. This is warm water cooling and falling down. What it kind of doesn't show very well that this is predominantly cold and a small amount of heat.
Okay.
And the
Thank you.
heat is on top and the bottom is very cold. And one thing to understand about these ocean currents is that for example, the Pacific is much less salty than the Atlantic. And because of that, the surface water never sinks. And so the entire Pacific is about 500 meters of water that's influenced by these heat transport. And the bottom, below 500 meters down to the bottom, that's coming from the poles and going to the poles. That's a different highway. It's a completely different system. They don't really mix. They
Okay.
barely interact. All of the action in the Pacific is in the top 500 meters. All of the stuff under that is just hauling up from the South Pole to the North Pole and then coming up and turning hot as it, turns into storms here, and also gives up heat and turns into storms here. This is a different conveyor belt. This is just going down and coming down, and this is underneath. So what's happening below, say 800, 1,000 meters is mostly water coming north and south, and hardly any of it affected by the sun. It's not nearly as mixed as we would think. And whenever you get salty water, you can penetrate that and go down. And
Okay.
it's really only salty water that can do that.
Thank you.
That makes sense? So look,
Yeah.
let me show you this. Here we have cold water getting warm, right? So it's coming up. What brings it up? The sucking brings it up. The low pressure of the water getting forced around here, this pressure leaves a gap, and that gap has to be filled by water coming up. And we saw that in the tank. We saw that cold water coming up because the hot water is sucking it by moving down, by moving away, moving south. So this is very similar to that tank that we saw.
Okay. Thank
Make
you.
sense?
Yeah, thank you.
And it's much more complicated than this. This is just the basic, ocean hydraulics, but I don't understand 90% of it.
Yeah. I'll have a look at, so the other thing is I'll have a look at the camera thing. I don't very much enjoy looking at my physical, but I'll try. Okay. Thanks.
Okay, I'm going to stop recording.
Thank you.